Okay, everybody, we're going to go in here on Module 3. Week 3, we're looking at probability. So we have several sections we're going to go through here on probability. First thing we need to define is something called a chance experiment and events. A chance experiment is any sort of a process in which we're making observations and from which two or more possible outcomes will result. But it's very important that we cannot predict which one of those outcomes will result. We know beforehand what the possible outcomes are. Those are events, but we can't predict which one will result. But we can determine how likely it is that one or the other will. For our example here is when we toss a single coin, there are two possible outcomes. So that is our chance experiment, is tossing the coin. The two outcomes, of course, will be heads or tails. We can't predict which one it'll be, but we can predict, the frequency or the likelihood of one or the other. Or we can look at selecting a single card from a deck of 52, a standard 52 card deck. We could get a ace, diamonds, whatever. We can predict the number of the card, the suit of the card, all sorts of things about that card, about that result that we cannot predict which it'll be, but we can say how likely it is that one or the other will result. Sample space, then, is a collection of all of those possible outcomes from that chance experiment. So like we said, we know beforehand what the possible results are. We just don't know which one is going to occur from that specific experiment. So we look at the sample space of each of these chance experiments. The sample space of a chance experiment can be represented in many ways. One representation is a simple list. So we could just list all the possible results that can come out. For a car purchase, chance experiment described it above. The possible outcome, so that car purchase was here. Customer is selected. A random customer is selected, and the chance of what type of car they're going to purchase is what we're looking at here. From right here. So we have Honda Civic is available, either hybrid or traditional engine. What will they purchase? So there are possible outcomes here. We could have a randomly selected customer, could be male and they could have bought a hybrid, could be female and bought a hybrid, could be male and bought traditional, or female and bought traditional, because those are the two things we're looking at, is whether they bought a hybrid or traditional motor engine car, and if they were a male or female purchaser. So we can list out our sample space simply by listing out those combinations. There's two different variables, and two possibilities for each variable, which gives us four possible combinations. We could also have done a probability tree. So we start out, first variable here you can see is gender. So we split the tree, male or female. And then the second variable is the type of engine. So we decide hybrid or traditional. And notice this one here, that's the male hybrid. Oops. This one would be male traditional, this one would be female hybrid, and this one would be female traditional. Just follow the branches from start to the end to get what that combination is. So to identify any particular outcome in the sample space, you just go through those branches in the tree, like we said, from the trunk out to the end of the branch, and it'll identify gender and type of engine. Events. So an event is any collection of outcomes. An outcome, remember, is any possible result of that chance experiment. A simple event is an event consisting of exactly one outcome. So we could have an event that consists of more than one outcome. So if any of those outcomes takes place, there's different ways to combine them. We can have them combined so that if any of those outcomes take place, then we're successful. Or maybe we have to have a specific combination of outcomes to be successful. So it's important on how those are combined if we're doing something other than a simple event. So let's consider a situation, buying the car again. Gender, male or female versus hybrid or traditional. Using this notation, one possible representation of the sample space is M for male, H for hybrid, F for female, H for hybrid, male traditional, female traditional. Because there are 4 outcomes, there are 4 possible simple events. Each single outcome is its own simple event. But what if we just care whether they buy a traditional transmission or a traditional motor or a hybrid? We don't care about the gender. Well, now we're looking at 2 possible outcomes, male and hybrid and female and hybrid. The first variable doesn't matter, so there's 2 of those simple events, or 2 of those outcomes that make up this now compound event, where either one of those would be true. Or we could focus on the other variable in our set here, which would be gender. Let's say we only care that the purchaser is male and not what kind of car they bought. They got male and hybrid and male traditional. Those 2 events are in that, or those 2 outcomes, I should say, are in that compound event. So we can combine these simple events to form new events. We could do it with let A and B denote the 2 events. The events that consist of, note A, not A would be the event that consists of all outcomes in the sample space that are not in event A. So not A is called the complement. So there's a couple notations. You have the not A, you have the A with the C, you have the A prime, which is read not A, or A with a bar over it. That bar is also read as complement. So A complement or complement of A. So combinations, A or B, this would be a union of events. So our event is successful. So it should be a union of outcomes, I should say. The event is successful if either A or B occurs. Doesn't have to be both. A and B is an intersection of events. Both have to occur. Now that term union and intersection actually come from a contingency table. The term intersection makes a lot more sense when you look at it in that table. We'll look at that later on. Let's say a traffic engineer has been asked to consider whether a stop sign at the bottom of a freeway off-ramp should be replaced by a traffic light. Suppose she were to record the turning direction, left or right, of each of 3 successive vehicles. This is a chance experiment. The sample space contains 8 outcomes. There's 3 different items here, and each has 2 possibilities. So that's 2 to the 3rd power. Left or right are the 2 possibilities, and it's being repeated 3 times with 3 different vehicles. So that's 2 to the 3rd power, which is 8. Notice there are 8 results there. Each of these outcomes determines a simple event. Other events include, so each of these back here was a simple event. All 3 could go left, the first one right, the next 2 left, and so on. These are now compound events. A is the event that exactly 1 car goes right. So that would be the first one could go right and the others left, or the second one could go right and the others left, or the last one, the 3rd one could go right and the others go left. B is the event that at most 1 of the cars turns right. So that would be the same as event A plus the possibility that all 3 of them turn left. So at most 1, so 1 or 0. And C, the event that all cars turn in the same direction. So that'd be either all 3 left or all 3 right. Now, these are not the only compound events. It's just a few examples that we listed out there. We could literally come up with hundreds of different compound events by combining those differently. But now event C was the event that all cars turn in the same direction. If we do not C, or the complement of C, that is everything else. So C was all 3 left or all 3 right. That's 2 outcomes there in that event. The other 6 outcomes then are part of not C, because those are all of the outcomes where it was not true that all 3 cars turned in the same direction. So A or C A was that exactly one turned right, and C was that they all turned the same direction. So you can see these are all of the outcomes that were in event A. These are all the outcomes that were in event C. We just put them all together. We unite them all in one big group. That's what's called a union. B intersect C, however, where B was the event that at most one car turns right and C was they all turn the same direction. Well, if you'll notice, all three going left is the one that was in both of them. B had all three left, and C had all three going left. Mutually exclusive. Mutually exclusive events are events that have no outcomes in common. In other words, it's not possible for both events to occur at the same time. So the term disjoint is also sometimes used. Again, that means they are disconnected. They have no events in common, no outcomes in common. Tried to switch my camera and it did not work here, so heading back to the other camera, sorry. There we go. Back on. Sorry about that. My other camera must not be fully connected. Okay, so a Venn diagram. A Venn diagram is just a visual representation of all of these outcomes within our sample space. So a simple representation here, this is inside that circle. The whole rectangle is the whole sample space, all of the possible events of the sample space. Inside the circle are all the outcomes that qualify or meet the requirements of event A. Everything outside the circle is everything else. That's not A outside the circle. Here we have events A and B. This circle contains all the items, all the outcomes that satisfy event A. This circle has all the outcomes that satisfy event B. Where they overlap, that would actually be A and B together. But this is, we want to know A or B. So it's A, B, or where they overlap. At least one of them has to occur, but it doesn't have to be both. Now the contrast down here where we have A and B, that's only true where both are true. So that's only true where they overlap. And then mutually exclusive events, notice A and B do not overlap at all. So it is not possible. Any event that includes outcomes from both A and B would not occur. And we can, of course, do the same with three different events to see how they overlap. A or B or C, any of the three is true or where they overlap. A and B and C, again, only where all three of them overlap would be true now. And then again, mutually exclusive or disjoint events. So here we have multiple events, not just two or three. Those events are mutually exclusive if no two of them have any outcomes in common. So there's no single outcome that is in more than one of them. There's our example. Some of our class has 4 students. The instructor has an unusual way of asking questions. 4 slips of paper numbered 1, 2, and 3 are placed in a box. The instructor determines the student to whom any particular question will be addressed by selecting one of these 4 slips at random. Suppose that one question is to be posed during each of the next 2 class meetings. One possible outcome would be represented by 3 and 1, where the first question was addressed by student 3 and the second by student 1. There are 15 other possibilities. The event that the same student answers both questions. Event A, so student 1 answers both, 2, 3, 4. The event that student 1 answers at least one of the questions. Well, answering both is at least one. Answering the first one, notice each of those 3 possibilities, student 1 answers the first question. That qualifies, or answering the second one. Those 3 possibilities are student 1 answering the second question and someone else answering the first. Option C here looks like that is the sum of the students would add up to 4. The number of the student adds up to 4 in each case, so 3, 1, 2, 2, or 1, 3. Option D here looks like either student 3 answers at least one question, and 4 would answer any others. So 3 answers both of them here, 3 answers one, 4 the other in each of those other cases. And again, there might be other descriptions that could go along with these. So the outcome 3-1 is contained in each events B and C. 3-1, 3-1. And there are only 2 common outcomes in all 3 events. E also has 1, 3, and 3, 1. So that is actually in all 3, B, C, and E. So the events C, D, and F are mutually exclusive because no events contained in either of them are in the other 2 events. So C, there's none of those are in D. Nope. And F, none of the items in C are in F. Well, none of the items in D are in F as well. So yes, those are truly mutually exclusive. No event that is in one is in the other. No outcome that is in one is in the other event. Moving on to the next section. Second to load up here. Okay, so continuing with our probability. Definition of what is probability. We've defined the events. So there's 3 different approaches to probability. One is the classical approach. And in the classical approach, or sometimes called the theoretical approach, we are looking at equally likely events. That's a very important term. That means each of the possible outcomes or events has the same likelihood of occurring. Like rolling a fair die. There are 6 numbers on that die, 1 through 6. Each of them is equally likely if that die is a fair die, meaning it'll come up the same amount on each of those 6 sides. So if that is true, the probability of an event occurring is the number of outcomes that contain that event over the total number of outcomes in the sample space. So like rolling a 2 on a fair die. There's only one outcome that contains a 2 out of 6 in the whole sample space. So it's a 1/6 probability, or 0.1667 if you divide it out as a decimal. So we can use this by simply counting outcomes that contain that event and counting total outcomes in the sample space. So we have 4 students, Adam, Bettina, Carlos, and Deborah, A, B, C, and D for ease, submitted correct solutions to a math contest that had 2 prizes. The contest rules specify that if more than 2 correct responses are submitted, the winners will be selected at random from those submitting correct responses. We use A and B to denote the outcome that Adam and Benita are the 2 selected. What other possible outcomes are there? There's Adam and Bettina, Adam and Carlos, Adam and Deborah. There's Bettina and Carlos, Bettina and Deborah, and Carlos and Deborah. Now, it's important that we ask ourselves, does it matter which one comes first? And as long as both prizes are the same, it does not. If the prizes were different, well then Adam and Bettina would be a different outcome than Bettina and Adam. But in this case, that's not true. It's the same prize for both people. So there was the same list we came up with. So suppose E denotes the event that both selected winners are the same sex, same gender. So that would be both Adam and Carlos or Bettina and Deborah. Those would be the 2 possibilities. So what is that probability that occurs? Well, there's 2 events in that, or 2 outcomes in that event out of 6 total outcomes. So 2 out of 6, or 0.333, is that possibility. Let F denote the event that at least one of the winners is female. Well, if we look at the outcomes back here, there's one that's female, one female, both are female there, and one female there. 5 out of the 6 contain at least one female student, for a probability of 0.833. Relative frequency approach, sometimes called the simulation or empirical approach. And what this is if we don't have that assurance that they're equally likely, we just repeat the experiment over and over and over again. And then we look at how many times a certain event occurred out of the total number of trials that we repeated the experiment. So if you look at a coin being described as fair, a fair coin is equally likely to come up heads or tails, so 50% chance either way. So fairness in 50%, would that necessarily be measured in 10 successive tosses? Well, if it were strictly that way, it should always come out to be 5 heads and 5 tails. But we know that that's not really true because, well, it's something called the law of large numbers that we'll talk about as we go on. That those probabilities really only are true over a large number of repetitions. 10 repetitions, 10 tosses of the coin is not enough. It's very possible to get 8 or 9 heads. Even 10 heads, not as likely, but it's possible to get all 10 heads in just 10 tosses of the coin. If you're tossing the coin 1,000 times, getting 1,000 heads in a row is very unlikely. Almost impossible. But at 10 tosses, it's unlikely, but plausible. But again, at that 1,000 tosses, we're more likely to get really close to 500 heads than we are simply in 10 tosses of getting exactly 5 heads. Because of that law of large numbers. It's a probability, it doesn't always have to work out over a small number of trials. So we're going to have our chance experiment where H is the coin landing heads and T is the coin landing tails. So it's a fair coin being tossed over and over again. So we look at the toss here, and what the result is, cumulative number of heads. So the first one was obviously not a head because there's a 0 there. Second one was obviously a head because there's a 1 there now. And you can see the cumulative number of heads. Well, the relative frequency is the percent, the probability of getting heads that would be represented by the frequency of this experiment. But only one flip that came up tails, well, that would seem to show that the probability of getting heads is 0. We know that's not true. And you can see how that probability bounces up and down here depending on each result. But as the number gets higher, even at 10 flips, it starts to stabilize. It doesn't jump up and down near as much. Getting a head as a result jumps the probability up a lot here at the beginning. Getting a tails drops it down a lot. But as we go, it jumps up and down less. Notice here, this is a graph where we repeat this experiment over and over again 50 times. And you can see at the beginning, probability is jumping way up and down. And as we get going, it stabilizes. Now, this appears to be stabilizing. If this is 0.5 or 50% here, this appears to be stabilizing somewhere slightly above 50%. So we would still want to continue this experiment for more than 50 tosses. But if that trend continues, this may not be a fair coin. This one here now, it is actually zeroing in as we get to 1,000. It appears to be zeroing in on that 50% or 0.5. And there's that law of large numbers as we mentioned. With a small number of repetitions, or the term is often used as trials. On a small number of trials, we can't reasonably expect the percentage of the outcome to be the true probability. But as that number of repetitions goes up, we expect that to approach the true probability of that event. So there is that relative frequency approach. The number of times that it occurs divided by the number of trials, the number of times the experiment was repeated. Subjective approach. Now, some people refer to objective probability as an educated guess. And that's true, but too many people put too much emphasis on the guess part of that and not on educated. An example of subjective probability this time of year, football season. They talk about the odds or chances on one team winning a game or whatever, and it's way more complex than that. But they look at in the past when these two teams have played, this team A has won 60% of the games. But then they look back and see, well, the starting quarterback for team A is hurt and isn't going to play, or maybe team B traditionally struggles in cold weather and it's going to be snowing that day. Or one of the teams struggles in wet weather, things like that. And they adjust. Now, the facts they're using to create this probability are all true, and there's numbers behind them. But it's how they weight them and combine them to get to a final result that is subjective. They have to decide how much weight to put on each of those factors to come up with that final probability. There is no exact science to it. Two people will approach a subjective probability and come up with different answers. But for example, an airline passenger might report their subjective assessment of the probability of being denied a seat as a result of overbooking. They might just say it's 0.01. Because it's close to 0, what they're saying is they think it's very unlikely. So when we come to subjective probability, those are the things to keep in mind. Remember that 0 probability means it's impossible. So if you come up with a probability close to 0, like 0.01, you're saying it's highly unlikely. And again, in subjective probability, that's one of the factors. If you come up with something close to 1, remember 1, a probability of 1 means it is definite. It is guaranteed. It's the only possibility. Nothing else could happen. So if you get a probability close to 1, you're saying you think it's pretty sure it's going to happen. So now, how are probabilities determined? So probability statements are frequently encountered in newspapers, magazines, and all that. What are they based on? Well, if it's the classical approach, again, remember we have to have those equally likely outcomes. If we have that, we can use the classical approach. The subjective approach, unfortunately, is the most common. Again, they are taking in some facts and some statistics, but they're combining them in a way that's left up to their judgment. Politics and news and stuff like that, most of those are subjective. And unfortunately, in most cases, especially in politics, but in other events too, there's also personal bias that comes into those subjective probabilities. And it goes, of course, relative frequency approach just looks at the past. How many times has this been done in the past, and how many times did we get this certain result? Okay, so on to section 3 here. So as we continue with probability, so basic properties of probabilities. For any event, probability of that event occurring is between 0 and 1. Remember we said 0 means it's impossible, 1 means it's guaranteed. If the sample space, if S is the sample space for the experiment, well, then the probability of P of S means the probability that something in the sample space will occur. Well, that's 1. It's guaranteed. Something in the sample space has to occur. The other way to think about it is if you added up the probabilities of all of the possible events in the sample space, they should add up to 1. If two events, E and F, are mutually exclusive, then the probability of getting E or F is just the sum of them. Remember, mutually exclusive means that the probability of E and F equals 0. There are no possible outcomes that are in both events at all. So can't possibly meet both events. So because of that, all we have to do is worry about each of them adding them together. We don't have to worry about the probability that they could both occur at once because they can't. They're mutually exclusive. And for any event E, the probability of that event and the probability of its complement add up to 1. That's a very useful tool when we are calculating probabilities. Sometimes it's easier to calculate the probability of the complement than it is of the event itself. So the probability of not E is equal to 1. That's the total probability of the sample space minus the probability of E. Or the other way around, the probability of E is equal to the total sample space, 1, minus the probability of the complement, or the not E. So the authors of the paper, Preventable Deaths Due to Problems in Care in Acute Hospitals, carried out a study in hospital deaths. They estimated 5.2% of deaths occurred in hospitals were preventable. They attributed those preventable deaths to poor patient monitoring, diagnostic errors, inadequate drug or fluid management, and other. 31% were due to poor patient monitoring, 30 were due to diagnostic errors, 21 were due to inadequate drug or fluid management, and 18 were due to other errors. Now, if you add those all up, you will see that they do add up to 100%. That makes up the whole sample space. That other category usually is what's used to make up that difference to make sure it equals 100%. So consider the chance experiments of observing a given type of error in a preventable death. So 01 is the error was poor patient monitoring, 2 was diagnostic, 3 was drug or fluid management, and 4 was something else. There's our table. This is called a probability distribution. Lists every possible outcome and its probability. Notice that again, that has to all add up to a total of 100% or 1.00. Now it follows P of E that E be the event that randomly selected preventable death is due to poor patient monitoring, diagnostic error, or inadequate fluid management. So that means any of those first three. But we could just add up those probabilities. The notation would be 01 union with 02, union with 03. Any one of those three. Or we could write it out in words of 01 or 02 or 03. Since they are mutually exclusive here, you can't die from two different causes. We're assuming, in this case, to simplify it. We just simply add up those probabilities, like we were saying, out of the table to get 0.82. Now, here's a case where it might have been simpler to do the complement. The 04, the other, is the only one not included there. So we could have done 1 minus 04, which would have been 1 minus 0.18 to get 0.82. That might have been simpler than adding up the three probabilities for the three that were included there. So again, they're talking about other ways of calculating it. You could have subtracted the complement from the whole sample space. So equally likely outcomes. So let's look at a chance experiment involving tossing fair coins, rolling a die, or selecting cards from a well-mixed deck. So these are all spots where there are equally likely outcomes. So here we're looking at, each outcome is just 1 over, has a probability of 1 over the total number of possibilities. If we have an event, again, an event can contain more than one outcome. Then we look at the number of simple events in E divided by the total number of possibilities in the sample space. Our addition rule. If they were mutually exclusive, addition rule applies to or union situations. Probability of E or F, if they're mutually exclusive, is just the probability of E plus probability of F. Now that is true only because the probability of E and F is 0 when they're mutually exclusive. If there's several events that are mutually exclusive, again, we just add the probabilities of those together. So what is the probability that any of these K mutually exclusive events occurs is the sum of the probabilities of each of the individual events. So a large auto center sells cars made by a number of different manufacturers, Honda, Nissan, and Toyota. For our chance experiment, we're going to assume they're equally likely. The outcomes to the sample space, actually we're not going to assume they're necessarily equally likely. The next car purchased that this auto center is a certain make. So the outcomes in the sample space would then be simple events such as Nissan, Altima, Toyota Prius, and so on. So let's define E1, E2, and E3 as Honda, Nissan, and Toyota. E1 is not a simple event because there are more than one Hondas. There's Civics, Accords, other different models of Honda cars there. So it actually includes several different outcomes in E1, but any of the outcomes that are made by Honda would fall into E1. Notice no cars are made by both Honda, Nissan, and Toyota. So each of those is still mutually exclusive. Then, of course, they give you the probabilities here. They've been estimated by past experience or whatever. Since when they say estimated, chances are those are subjective probabilities. So because they're mutually exclusive, the addition rule applies. Probability of Honda or Nissan or Toyota, we just add up the individual probabilities to get 0.57. Now what that is telling us, these are the probabilities given here, is that that dealer has other manufacturers to sell, but we're just not looking at anything outside of Honda, Nissan, and Toyota right now. Probability that the next car purchase is not made by one of these three manufacturers. Well, one would be the whole sample space. The chances that it was made, the next car is by one of those manufacturers was 0.57, so we subtract that from the whole sample space to get 0.543. That is the complement of that original probability. In other words, that it's not one of the three that we listed. So continuing on probabilities, conditional probabilities. So conditional probabilities mean we already know something about the outcome. And so what's the probability of the rest of the event being true, given that we know part of it's already true? I'm going back to the hybrid versus traditional cars. How would the probability of the car being hybrid or traditional change if we knew the purchaser was female? That would be a conditional probability. We already knew something about the outcome. We're just looking at what the other characteristics are then. So here, sometimes knowledge that one event has occurred changes our assessment of the likelihood that another event will occur. So for example, consider a population in which only 0.1% of all individuals have a certain disease. It is difficult to tell if someone has the disease based on a physical exam, but there's a diagnostic test. Unfortunately, the test is not always correct. So, of those with positive tests, 80% have the disease, and the other 20% is a false positive. So, let's look at, spell it right here. Those that have the disease, those that do not have the disease, and let's say they test positive or negative. Well, for those that test positive, 0.8 have the disease and 0.2 do not. So that's what this is saying. Now, we don't have the breakdown of negative test results at this time. Now, I'm let E. So in this case, we're going to know that the person tests positive is the event that they actually have the disease. Well, P of E, as we just saw, is 0.8. And F is the event that the test was positive, but they do not have the disease. F is the event that the test is positive, So what they're saying here, what is the probability that they have the disease that we know, that once we know that their test is positive? And that's where the 0.8 comes in. So if we know they had a positive test, the probability that they have the disease is 0.8. And that is the notation. That bar is saying, given that we already know that they have a positive test, what's the probability that they have the disease? And there is that breakdown. The probability that they have the disease is only 0.001. The probability that they have the disease, given that we know that the test was positive, goes up to 0.8. So we've narrowed down our search. We're not looking at the whole population anymore. We're only looking at the portion of the population that had a positive test. So what this means is, before we have the test information, the occurrence of E is very unlikely. But once we have the results of the test and know that it's positive, then the chances of that event E, of having the disease, go up dramatically. If this were not the case, of course, it wouldn't be a very good test. Conditional probability, some of the math behind it. If the events are independent, the probability, or sorry, I should not say independent. If the events follow our normal probability guidelines, conditional probability, suppose that E and F are two events, the conditional probability of event E given that F has occurred is the intersection of E and F, the probability of both occurring divided by the probability of F. So in this example, let's do medical guidelines recommend that a hospitalized patient who suffers a cardiac arrest, a series of conditions where the heart stops, a serious condition where the heart stops beating, should receive defibrillation and electric shock to the heart within 2 minutes. Delayed time to defibrillate after hospital cardiac arrest describes a study of the time to defibrillate in hospitals of various sizes. So here's our table of giving the data from those results. So here we have event S is the event that a selected patient is at a small hospital. M is the event that they're at a medium size. L that they're at a large. D is the event that the selected patient received defibrillation within 2 minutes or less. Well, P of D is the probability that they received the defibrillation within 2 minutes or less. 4,689 patients out of all the 6,716 that they looked at received the defibrillation within 2 minutes. That's a probability of 0.698, so just under 70%. Now, this is a probability is interpreted as the proportion of hospitalized patients who had cardiac arrest and received defibrillation within 2 minutes. Now suppose it is known that a selected patient was at a small hospital. So to look at this, we are now going to look at just narrowing it down to those patients at a small hospital. The formula for this probability that they received defibrillation within 2 minutes, and given that we knew they're at that small hospital, is the probability of getting defibrillation within 2 minutes and being at a small hospital divided by the probability of being at a small hospital. So we look here, let's say there were 1,124 patients that were both at a small hospital and received their defibrillation within 2 minutes. That's all of the patients, the 6,716. That's a probability of 0.167. Probability of being a small hospital is 1,700 out of the 6,716. That's 0.253. We divide those to get 0.660. Now let's go back here. This was 0.698. That probability appears to be slightly smaller. Now, at this point, we would probably say that it is slightly less chance to get defibrillated within 2 minutes at a small hospital. Later on in the course, we'll look at, is that difference really significant? Yes, it's off by like 0.03, but is that really a difference, or is it just that in this sample we happen to have one or two less in the small hospitals? That difference has to be large enough that we can say that it truly is a difference and not just a result of the particular sample we happen to be working with. So there's two other conditional probabilities of interest here. Probability of getting defibrillated within 2 minutes at a medium hospital, well, that's 0.711. And in a large, that's also 0.711. Now, the fact that those two are exactly the same seems to indicate they're pretty close to the same chance of getting defibrillated within 2 minutes. You might say that reinforces the probability that you're less likely to get timely defibrillation in a small hospital, but again, we don't have that capability of really analyzing that right now. What's the probability that you were at a large hospital given that you were defibrillated on time? Now, notice that is the reverse of this probability, and it's going to give us a much different result. still the probability of being at a large hospital and getting defibrillated on time. That's the same probability as before, but now it's instead of the number of people in the large hospital, it's the number of people that got defibrillated on time that we're looking at. So that's a much different probability. So knowing that they got defibrillated on time, 0.296 of those, or just under 30%, were at large hospitals. And there are other conditional probabilities that we can go through, and this is just a breakdown. Seeing that probability of being defibrillated on time and given you're at a large hospital is a much different probability than the probability of being at a large hospital given that you were defibrillated. They are not symmetric. So notice the difference between these conditional probabilities depending on which one is the condition and which one is the probability of interest. The reference point for unconditioned probabilities is the entire group. So that's all of the patients that were in the sample, whereas the conditional probabilities narrows it down to a specific group. And of course, the specific group that we narrow it down to changes the probability. Next on our list, more with probabilities, independence. Independent events is where the probability of one event occurring does not change if we know that another event has already occurred. I'm like rolling a die and flipping a coin. If we flip the coin and get heads, that does not change the probability of rolling any of the numbers on the die. So here we have a joint probability table, sometimes called a contingency table, where we basically show two variables. On top here we have single family, condo, and multifamily homes, different types of homes. And the type of mortgage, whether it's an adjustable mortgage or a fixed mortgage that we're looking at. And you'll see here, this is the total. 50% of the families are from single family homes. Now, as we go on, we want to look at the conditional probabilities. If E is the event that they are adjustable rate, F is the event that the mortgage is for a single family house. The probability of being an adjustable rate given that it's a single family home. Well, probability of being both adjustable and single family, that's right here, that's the 0.4. And the probability of just being a single family home, well, that's this total down here, 0.5. So that's 0.4 over 0.5 or 0.8 probability. Well, 80% means 80% of the loans for the single family houses are adjustable rate loans. Now, notice that the other way around, the probability that it is the unconditioned probability of the event E is 70%. If we look at the probability of being a single family house given that it was adjustable rate, it would be 0.4 over 0.7, which is 0.571. That's just reversing it. Here it was E given F, here it's F given E. Notice the top number stays the same because that top number is just E and F. The bottom number changes because we're looking at a different section of the entire population. So we could look at the probability of being adjustable rate given that it's a condo. That's also 0.7. Notice the fact that those two are the same means that, well, the type of mortgage is independent of the type of household. So the probability of having an adjustable rate mortgage given that it's single family is the same as the probability of just having an adjustable rate mortgage out of all of the homeowners. And that would be true for each of the different types. So here they're saying the type of home owned is or the type of loan, whether adjustable or fixed rate, is independent of the type of home owned. So that means all those probabilities, probability of having an adjustable rate mortgage would be the same no matter what type of home you're looking at. So these are different identities that occur with our conditional probabilities. If they're independent, if the events E and F are independent, well, then we would expect the probability of E given F to just equal the probability of E. Well, then all the other probabilities, the condition here would have no effect on the initial probability. So whatever the final probability is, it's just going to be the initial probability. The event, or the conditional, does not restrict the population at all. Okay, I think that is all I really want to do on independence with you. So we're going to go ahead and skip out of there. I do want to talk about replacement and not replacement here. So sampling with replacement means once selected, the object or the possibility is put back into the sample space, into the population, before we draw the next one. I mean, think of this as drawing marbles out of a box. If you have 3 red and 2 blue marbles in a box, if I draw out 2 marbles, and I want to know what's the probability, both of them are red. Well, if I draw out the first one is going to be 3 out of 5. The second one depends on whether I put the first one back first. If I put the first one back in and mix them up again before I draw the next one, the second one is going to be 3 out of 5. If I don't, this would be with replacement. Without replacement, the first one would be 3 out of 5, but the second one, now there's only 2 red, and there's only 4 total marbles. So now that would be 2 out of 4. So without replacement, you draw the first one, you record it, and you set it aside. You do not put it back in the population before you draw again. Because of this, when you're sampling without replacement, your probability changes from 1. So consider selecting 3 cards from a deck of playing cards. It can be done 2 ways. You can shuffle the cards and then deal out 3, or you can pull out 1 card, put it back in, shuffle again, pull out another, and this would be with replacement. Of course, if you pulled out all 3 cards at once, that would be without replacement. So from the standpoint of probability, with and without replacement are analyzed very differently. So let's consider 3 events here. The probability that the first card is hearts, the probability the second card is hearts, and the probability that the third card is hearts. With replacement, H3 is 0.25 because regardless of whether 1 and 2 occurs, the third card, there's still going to be 13 hearts in the deck out of 52 because you put the first 2 back in. But if it's done without replacement, H3 depends on whether you had hearts in 1 or 2 because those are now out of the deck. So if it's with replacement, the events are independent. If it's without replacement, then the probabilities will change depending on what the results of the first 2 events were. So the probability of H3, if it's without replacement, depends on H1 and H2. If H1 and H2 occurred, then there's only 11 hearts left because out of 13, 2 have already been drawn, and only 50 cards left in the deck, giving us a probability of 0.22. If it's both H1 and H2 did not occur, in other words, neither one of those first 2 cards were hearts, then there's still 13 hearts in a deck of only 50. The probability changes to 0.26. So you can see the probability can change drastically depending on the results of the first 2 cards. So that is the importance of replacement and not replacement. Finally, sorry about the clunkiness here. The textbook chooses to break things up into little pieces. So some general rules of probability. The addition rule. Now, we looked at the addition rule for mutually exclusive events. that assumed the two events could not occur together. Here, what if they're not mutually exclusive? Well, then the probability of E or F is the probability of E plus the probability of F. But then we got to subtract out the probability they both occurred together. Because remember that Venn diagram, we've counted this overlap here twice, so we got to subtract it back out. And again, this is because if they're mutually exclusive, probability of E and F is 0, so we didn't have to subtract it out. Now we have to account for the fact that it would have been counted both in event E and in event F. So we got to take it out since it's been subtracted twice. So suppose that 60% of all customers of a large cable company subscribe to internet, 40% subscribe to phone, 25% have both. If E is the event the customer has internet and F they have phone, probability of E or F is the probability of having internet plus the probability of having phone minus the probability they have both. Again, those were counted in both of these, so we had to subtract it out since it's been counted twice, giving us that probability of 0.25. The event that the customer has neither type of service would be the complement of that. This is that they have one of the two services or more. So 0.75 is probably to have at least one service, phone or internet. Probability they have neither is the complement. So 1 minus the 0.25, which is going to give us, 1 minus the 0.75, I should say, which is going to give us 0.25. Again, this is the Venn diagrams that go with that. Now, there are a lot of ways we could go about doing these. You can see here, if we're going to combine 3 events, well, then we got to subtract out the overlaps and look back. This is the Venn diagram. I don't know if I had that one up here. We do not have the triple Venn diagram, but what that is saying, so let's say here's event E, here's event F, and here's G. So we add E, F, and G, probability of E, probability of F, probability of G. Well, that gets this overlaps spots here more than once. So we subtract out E and F. So that subtracts out this section. Subtract out E and G. Well, that subtracts out this section. Notice this section's been subtracted out twice. Well, it was counted 3 times, so that's okay. Then we subtract out F and G. That's this section here. Notice this section now has been subtracted out 3 times. Well, it was only added in 3 times, so it's gone completely. So we do have to go back and add that section in once to get it back there. Typically, this is easier if you have this listed on a contingency table and you can just determine which pieces you want to add together. I looked at that in the meat session that we do this week. We'll look at that more closely. Multiplication rule for an intersection of events. So probably that both E and F occur. Or sorry, this was the multiplication rule. This was the 2 events that or occurs. So E or F is adding them together and subtracting out the probability that both occurs. How do we find that probability that both occurs if we're not given that? Well, we need to know whether they're independent or not. So suppose that 20% of all teenage drivers in a certain county receive a citation for a moving violation in 2018. Also suppose 80% of those receiving the citation attended traffic school so that they would not appear on their driving record. If a teenager from this county is selected, what is the probability they received a citation and attended traffic school? Well, if receiving the citation and attending traffic school are independent, that probability of, we'll let E be the probability they went to traffic school and F be the probability they got the citation. Probability of E intersect F is just the probability of E times the probability of F. Or general probability rule, even if they're not independent, it'd be the probability of E times probability F given that E has occurred. So here, 80% that they got us the citation, or sorry, that they went to traffic school, 20% that they got a citation, 16% overall. And we already talked about law of total probability, so that brings an end to our basic lecture for this week. So I am going to end it there. We will, like I said, we'll go over more details in our meet session this week. If you have any questions, please let me know. Otherwise, you have a great week.